Hi everyone. So now we discuss some questions from spectroscopy techniques, and that is NMR spectra, IR, microspectra and Raman spectra, and based on Lambert's Beers learning. Okay, based on these concepts, we'll discuss some questions. Okay, first question. This is given in last time Tsgenco exam, direct question given. Matching is given, list 1 and list 2. Match list 1, IR absorption bands. IR absorption bands is given in list 1. In list 2, functional groups given, corresponding functional group is given. So we have to see correct matching. So A, B, C, D. So 3200 to 3600, 2225. Okay, all are given in centimeter inverse. Next one 1710 centimeter inverse and 2950 centimeter inverse. Here CH3, OH, CN and C double bond O. Okay, like this given. Okay, so this type of questions, if one or two are known to us, from the options we can easily attempt them. So options given like this, and A, B, C, D, they are given like this, and 2, 3, 1, 4. A, B, C, D given 2, 3, 1, 4. Next to 2, 3, 4, 1. 2, 3, 4, 1. 4, 2, 3, 1. 4, 2, 3, 1. And 4, 2, 1, 3. So I have given some of the functional groups corresponding vibrational frequencies. Okay, what about the C double bond O group? And C double bond O group is around 1700. OH group is around 3200 to 3600. So we have A2C4. A2C4. If you see A2C4, that is given only in option 2. A2C4 given only in option 2. And that means B3N. So C triple bond N. Its vibrational frequency is 2225, and CH3 vibrational frequency is around 2950. And some other functional groups vibrational frequencies I have given already. Once you check, like C double bond C, C triple bond C, C single bond C. Okay, those vibrational frequencies also you may check once. C double bond O, C double bond S. Okay. So direct question given. Next one. This is given in set exam. This is given in set exam. The rotational spectrum of a diatomic molecule. The rotational spectrum of a diatomic molecule gives several lines. Some of these lines are located at. Okay, rotational spectrum of diatomic molecule is given. The lines are observed at 2021, 2024, 2027, 2030, 2033 centimeter inverse. So what is the rotational constant in centimeter inverse? That is the question given. Okay, what is the rotational constant? So if you take a rotational spectrum for diatomic molecule, the gap between any two successive spectral lines is how much? 2b. The gap between any two successive spectral lines is 2b. So 0 if you take for reference, various spectral lines are observed at 2b, 4b, 6b, 8b, like that, we'll get it. So the gap between any two successive lines you may take. 2b value is given how much? 3 centimeter inverse. So that means b value is 1.5 centimeter inverse. So b value is 1.5 centimeter inverse. Rotational constant value is 1.5. Okay. Next one. This is also given in Tsgenco exam. Last time Tsgenco exam from NMR spectroscopy. So from NMR spectroscopy itself, two questions given. Two questions given. Totally from spectroscopy 5 questions given. From NMR 2 questions. IR already we discussed 1 question. 1 question from mass spectra is given, and 1 question from UV visible spectroscopy is given. Okay, this is from NMR spectroscopy given. An organic ester with molecular mass 88. An organic ester with molecular mass 88 has PMR data as follows. Has PMR data as follows. It is given like this. A triplet at 1.23 delta, that is corresponding to 3 hydrogen atoms. The second one, a singlet, this is the data given, a singlet at 1.97 delta, that is corresponds to again 3 hydrogen atoms. The third one is a quartet at 4.06 delta, that is corresponds to 2 hydrogen atoms. The compound is, it is given like this only. Isopropyl formate, options given, isopropyl formate, methyl propionate, N-propyl formate, and fourth one, ethyl acetate. Okay, once you write all the structures and you may check, and I am going to direct option. So ethyl acetate, for example, if you verify ethyl acetate, that means CH3, C double bond O, CH2, CH3. We have. So how many types of protons we have here? 3 types of protons we have. The bonding connectivity of this proton, these protons, and these protons are different. So 3 types of protons we have. So how many signals we will get? 3 signals we will get. That is matched. 3 signals matched. Another one is in A set, how many protons are there? 3 protons. In B set also 3 protons. In C set 2 protons. See here, 3, 3, 2 protons. 3 protons, 3 protons, and 2 protons. That is also matched. Next one, coupling. If you consider spin splitting, here A type of protons are singlet, since the gap between these hydrogen atoms and these hydrogen atoms is high, so it may not undergo coupling, and so further splitting may not observe. So for this we will get singlet. So one singlet is given or not? Yes, one singlet is given, that corresponds to 3 hydrogen atoms, right? So next one, these 2 hydrogen atoms may couple with 3 protons. So therefore for this we will get what? Quartet. A quartet that corresponds to how many hydrogen atoms given? 2 hydrogen atoms. Next, B type of protons, if you take, how many neighboring protons are there? 2 neighboring protons are there. So we'll get n plus 1 lines. Okay, n plus 1 lines. The general expression is 2ni plus 1. Okay, for proton NMR spectroscopy, I is equal to 1 by 2, so n plus 1 we will get. So for B type of protons, 2 plus 1, that means 3 lines we will get. 3 lines means a triplet. Okay, that corresponds to 3 hydrogen atoms. So that is what ethyl acetate. Next, this is another question given in last time Tsgenco exam from NMR spectroscopy. In a given organic compound, comma, 2 kinds of protons exhibit signals at, 2 kinds of protons are present. They exhibit signals at 50 edges and 200 edges. Okay, in a given organic compound, 2 kinds of protons exhibit signals at 50 edges and 200 edges from TMS, tetramethylsilane reference compound, using a 60 megahertz NMR instrument. On 60 megahertz NMR instrument, what would be their equivalent positions in terms of edges? What would be their equivalent positions in terms of edges using 90 megahertz instrument? Using 90 megahertz instrument. So what about chemical shifts in edges using 90 megahertz instrument for the same protons and both protons? Options given: 75 and 300 edges, 75 and 300 edges, 60 comma 250 edges, 40 comma 260 edges, 90, 300 hedges, like this options given. So we know chemical shift in hedges depends on instrument frequency. Okay, so on 60 megahertz instrument it is 50 and 200. On 90 megahertz instrument we may get different values. But chemical shift in ppm is independent of instrument frequency. Chemical shift in ppm is independent of instrument frequency. So first we calculate chemical shift of these protons, two protons on 60 megahertz instrument in ppm. Okay, so chemical shift of first proton in ppm. In ppm, what is the formula we have? Chemical shift in hertz by instrument frequency in megahertz. Chemical shift in hertz by instrument frequency in megahertz. That means we are getting 5 by 6. Next, chemical shift of second compound in ppm. We are calculating in ppm. What is the formula? Chemical shift in hertz, that is 200 by instrument, okay, frequency in megahertz, and that is 60. We are getting 20 by 6, and or we can write 10 by 3 also. Okay, this we are getting it. And now on 90 megahertz instrument also will get what? Same chemical shift in ppm. So if you apply on 90 megahertz instrument, now if you apply on 90 megahertz instrument for first compound, okay, sorry, for first proton, chemical shift in ppm is 5 by 6. That is equal to chemical shift in hertz we want to calculate by instrument frequency is again what? 90 megahertz. Okay, so therefore 15 times gets cancelled. So chemical shift of first proton in hertz we are getting what? 15 into 5, 75. 75 we are getting. 75 given only in the first option. 75 given only the first option for second proton. No need to calculate it. Okay, anyhow, if you see on 90 megahertz instrument, what is the chemical shift of second proton in hertz? So what is its chemical shift in ppm? 20 by 6. 20 by 6 is equal to chemical shift in hertz by instrument frequency, that is 90. So 15 times gets cancelled. 15 into 20 will get 300 hertz. So like this is how to calculate it. Next one, Andy. This is previous CSR question for 2 marks. The Q band in the vibrational spectrum of acetylene is observed in the Q band in the vibrational spectrum of acetylene is observed in the CC stretching mode. CC stretching mode. Okay. CC stretching mode. CH symmetric stretching mode. Symmetric stretching mode. Third one, bending mode. Bending mode. CH anti symmetric stretching mode. Okay, acetylene given, and for acetylene when we will get Q band? For acetylene when we will get Q band? We know acetylene is a linear polyatomic molecule. Acetylene is a linear polyatomic molecule. We know for parallel vibrations, delta J is equal to plus or minus 1, whereas for perpendicular vibrations, parallel vibrations means corresponding to stretching vibrations. Bending vibrations means perpendicular vibrations means corresponding to bending vibrations. So what is the selection rule we have? Delta J is equal to plus or minus 1. So delta J is equal to plus or minus 1 means P and R branch lines we will get. Here PQR branch lines we will get. That means Q branch line corresponds to what? Perpendicular vibration or bending mode. So here the question is when we get Q band, that is corresponds to what? Bending mode. That is corresponds to what? Bending mode or perpendicular vibration. These are the selection rules for linear polyatomic molecule. Okay. Next one, this is previous CSR question at 4 marks. So from CSR also I am giving some simple questions only. Here I am explaining some simple questions only. In IR spectrum of COCN taken 5 H3 minus. In IR spectrum of CO, Cn taken 5 H3 minus. The COH stretch is observed at 1840 centimeter inverse. The vibrational frequency for COH is given as 1840 centimeter inverse. Then the COD stretch in CN taken 5D3 minus will appear at nearly options given 1300 centimeter inverse, 1400 centimeter inverse, 1500 centimeter inverse, and 1600 centimeter inverse. Okay, COH stretching frequency is given as 1840 centimeter inverse. Then what about COD stretching frequency? We discussed HBR and DBR. What about the vibrational frequency of DBR and HBR? And vibrational frequency of DBR is 1 by root 2 times 2 vibrational frequency of HBR. So whenever hydrogen atom is replaced by deuterium, the vibrational frequency decreases by 1 by root 2 times n. Similarly here, the vibrational frequency of COD is equal to 1 by root 2 times vibrational frequency of COHn. That means vibration frequency is given how much? 1840 by 1.414. 1840 by 1.414. If you do nearly, how much will get? 1300 centimeter inverse we will get. So it is option 1. Okay, next one. Similar type of question given in CSR. And the rotational constant and the fundamental vibrational frequency. Rotational constant and the fundamental vibrational frequency of HBR are 10 centimeter inverse and 2000 centimeter inverse respectively. Rotational constant and vibrational frequency for HBR given. The corresponding values for DBR are. The corresponding values for DBR are. So what about the rotational constant for DBR and vibrational frequency for DBR? So we know for reduced mass for DBR, okay, is double to reduced mass for HBR. I is directly proportional to mu, so IDBR is equal to 2 into IHBR. But B is inversely proportional to I. B is inversely proportional to I. So therefore B for DBR is equal to what? 1 by 2 times 2 B for HBR. Okay, B is equal to H by 8 pi square IC we have. So inverse relationship in between B and I. So BHBR is given 10. So 10 by 2, that means we'll get 5 centimeter inverse. Okay, and already we discussed nu DBR is equal to 1 by root 2 times nu bar HBR, that means 2000 by 1.414, 2000 by 1.414, nearly we will get 1410, nearly we will get 1410. Okay, this is about rotational constant for DBR and vibrational frequency for DBR. Okay. So next one. So the NMR spectrum of AX3, the NMR spectrum of AX3 exhibits lines at delta means ppm scale, 2.1 and 2.3 ppm for X type of protons. The NMR spectrum of AX3 exhibit lines at 2.1 and 2.3 ppm for X type of protons, and delta is equal to 4.1, 4.3, 4.5 and 4.7 ppm for A type of protons. Okay, here X type of protons 3 are there, so 3 plus 1, 4. 4 lines we will get for A, 4 lines we will get for A, and For X type of protons, one A is there, so 1 plus 1, 2. Doublet we will get it. Okay. So on 100 megahertz instrument, the data is given on 100 megahertz instrument. The question is the chemical shift in ppm of A, the chemical shift in ppm of A and X protons. What is the chemical shift of A and X protons in ppm and coupling constant J, coupling constant in H respectively R. So what is the chemical shift of A, what is the chemical shift of X, and what is the coupling constant in H? That is the question. Okay. So okay, options given 4.4, 2.2, 20, 2.2, 4.4, 10, 2.2, 4.4, 5, 15, 5, 5, okay, 5, 4.3, 2.1, 20, like these options given. Okay. You see for X type of protons we have what? A doublet. Doublet. So doublet, whenever we have a doublet, what we have to take? We have to take center. Center as its a chemical shift, and center we have to take as its chemical shift. So for X type of protons, the two lines are observed at what? 2.1, one is at 2.1, another one is at 2.3. That means the center is what? 2.2. 2.2. For A type of protons, okay, sorry, X type of protons, chemical shift is 2.2. That is given only in option 1. And chemical shift of X in ppm 2.2, that is given only in option 1. Option 1 is correct. Okay. Now if you verify for A type of protons, what we have? A quartet. Intensity is what? 1:3:3:1. 1:3:3:1. So center point we have to take. So they are observed at what? This line is observed at 4.1. Next one 4.3. So next one 4.5. Next one 4.7. So that is at in between 4.3 and 4.5. That means 4.4 we will get. Center we have to take it. Chemical shift means what? 4.4. Chemical shift is 4.4. Next, coupling constant. And coupling constant means the gap between any two adjacent lines in the multiplet, that is called coupling constant. The gap between any two adjacent lines, the gap between 2.3 and 2.1 is what? 0.2. 4.1, 4.3, 0.2. So we are getting 0.2 ppm. J value is 0.2 ppm, but the question is in hertz on 100 megahertz instrument. On 100 megahertz instrument, 1 ppm is equal to 100. So 0.2 ppm means 0.2 into 100. So we will get 20 hertz. 20 hertz. That is option 1 is correct. Okay. They are giving this type of questions repeatedly. Okay, next one. This is also previous year's question. The vibrational energy levels V dash is equal, V double dash is equal to 0 and V dash is equal to 1. The vibrational energy levels V double dash is equal to 0 and V dash is equal to 1 of a diatomic molecule are separated by 2143 centimeter inverse. So the gap between 0 and first level is given as 2143 centimeter inverse. Its enharmonicity omega E XE is 14 centimeter inverse. Its enharmonicity omega E XE is given as 14 centimeter inverse. The values of WE in centimeter inverse, and first to overtone in centimeter inverse of this molecule respectively are. So the gap between 0 and first level is given, omega E XE value is given, what is WE and what is where we will get first to overtone in centimeter inverse, we have to calculate it. So options given 2143, 4286, 2157, 4286, 2157 comma 4314, 2171 comma 4258. Okay, we know 0 to 1 is nothing but what? Fundamental transition. For fundamental transition, what is the gap? We have omega bar e into 1 minus 2xe. That is given as 2143. So omega bar e, we indicated with omega bar e, but here mentioned as omega e. So omega bar e into 2 omega bar e xe. That is equal to 143. But omega xe value is given 14. So omega bar e is equal to what? 2143 plus 14 into 2, 28. 2143 plus 28, we will get what? 2171. 2171 centimeter inverse. That is option 4. 2171 given only in the fourth option. See, from like this we can filter and some options. And so right here, no need to verify second question and first overturn where we are getting first overturn, no need to verify. Since 2171 given only in the fourth option. Okay, and we know for first overtone that is observed at omega 2 omega bar e into 1 minus 3xe. Second overtone 3 omega bar e into 1 minus 4xe. Hot bands omega bar e into 1 minus 4xe. Okay, so 2 omega bar e minus 3xe, and so 2 into omega bar e value 2171. Next minus 3 into 2, 6 we are getting. 3 into 2, 6 we are getting. Omega bar e xe value given 14. Okay, so 4300 change we are getting 28. If you subtract, you may get this one, 4258. Okay. Next one. For a diatomic molecule AB, the energy for the rotational transition, from J is equal to 0 to 1 state is 3.9 centimeter inverse. J is equal to 0 to 1 state. Okay, the energy required is given 3.9 centimeter inverse. Rotational transition is mentioned. So the energy for the rotational transition from J is equal to 3 to 4 state would be, okay, if the energy required for rotational transition from 0 to first level 3.9 centimeter inverse, then what is the energy required for 3 to 4 transition? Options given: 3.9 centimeter inverse, 7.8 centimeter inverse, 11.7 centimeter inverse, and 15.6 centimeter inverse. Okay, what is the expression for rotational energy levels? And Bj into J plus 1. You see delta E, and for first one E1 minus E0. E1 is equal to what we will get? 1 plus 1, that is 2B minus 0. So 2B value is given as 3.9 centimeter inverse. Now we want to calculate energy gap between what? Fourth level and the third level. The energy required is nothing but the gap between those two levels. E4 means what we will get? 4 plus 1, 5, 5 into 4, 20B minus E3, and 3 plus 1, 4, 4 into 3, 12 would be. That means we are getting 8B, and 8B means 4 into 2B. 4 into 2B, 2B values we got 3.9. So 4 into 4, nearly 16. That is 15.6 centimeter inverse we will get. Okay. Next, this question given and what is the selection rule for harmonic approximation? What is the selection rule we have for harmonic approximation? Delta V is equal to plus or minus 1. And selection rule for harmonic approximation is delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3. Okay. So sometimes they are giving direct questions based on selection rules also. Okay, this already I explained. H1 and MR spectrum of HD will show. H1 and MR spectrum of HD will show. Option singlet, doublet. Options given: singlet, doublet, triplet with 1:2:1 ratio. Triplet with 1:2:1 ratio. Triplet with 1:1:1 ratio. Next one, singlet. doublet. Proton NMR spectra we have to verify. Proton NMR spectra. So what is the neighbor and D? Neighbor is D. How many D atoms are there? Only one D atom is there. So the number of lines obtained is 2Ni plus 1. Okay. Due to coupling of this proton with the deuterium atom. How many deuterium atoms are there? Only one. What is the I value for deuterium? 1. So we'll get how many lines? 3 lines. 3 lines. But Pascal triangle is applicable to only proton NMR spectroscopy and proton NMR spectroscopy. Here we have only one deuterium atom. In the proton NMR spectroscopy, one H may couple with 2 H atoms. For these 2 H atoms, these are the possibilities. Okay, the possibilities are like this: 2 upward, 1 upward or downward, 2 downward. Okay, 1:2:1 we are getting like that. 2 hydrogen atoms, but here we have only one deuterium atom. That's why we will get the intensity ratio 1:1:1 and triplet with 1:1:1 intensity. Okay, since here the splitting is due to only one deuterium atom, the splitting of H proton signal is due to only one deuterium atom. Next, this is given in the vibrational spectrum of CO2, the number of fundamental vibrational motions in the vibrational spectrum of CO2, in the vibrational spectrum of CO2, the number of fundamental vibrational modes common in both IR and Raman. How many signals are common in IR and Raman? How many signals are common in IR and Raman? Options given: 3, 2, 1, 0. We know CO2 is an example for what? Centrosymmetric molecules. For centrosymmetric molecules, according to rule of mutual exclusion, IR active vibrations are Raman inactive, IR inactive vibrations are Raman active. So that means no common lines present in IR and Raman. So the number of common lines are 0. Okay, the number of common lines are 0. Similar type of question given like this: a triatomic molecule of the type AB2, a triatomic molecule of the type AB2 shows 2 IR absorption lines, and 1 IR Raman line. The structure of the molecule is: a triatomic molecule of the type AB2 shows 2 IR absorption lines and 1 IR Raman line. The structure of the molecule is. Options given like this: BBA, BAB, BBA, ABB. So here in the given data, if any common lines are present, that is not mentioned, and common lines are present, that is not mentioned, that means it may be centrosymmetric molecule, and it may be centrosymmetric molecule. So centrosymmetric molecule means that is given only in the option 2. Okay, so the given data, if any common lines are there in IR and Raman, that is not mentioned. No common lines means it may be centrosymmetric molecule. So that center of inversion is present only in option B and. Okay. This question given in an MR spectroscopy, the product of nuclear G factor G, nuclear magneton mu(n) and the magnetic field strength B0 give the. In an MR spectroscopy, the product of the nuclear G factor, nuclear Bohr magneton mu(n) and the magnetic field strength B0 give the. Options given: energy of transition from alpha to beta state, energy of transition from alpha to beta state, chemical shift, spin coupling constant, coupling constant J. Fourth one, gyromagnetic ratio gamma. Gyromagnetic ratio is nothing but what? It is the ratio of mu to I, magnetic momentum to spin angular momentum. So GB mu n gives what, and that is nothing but delta E. Whenever we are taking proton under the influence of magnetic field, we will get alpha state, upward orientation, beta state, downward orientation. What is the energy expression at E1 is equal to minus 1 by 2 GB mu n. Okay, E2 is what? Plus 1 by 2 GB mu n. So delta E, energy of transition. Delta E is nothing but energy of transition. The energy required for spin inversion. E2 minus E1, what we will get? GB mu n we will get. GB mu n we will get. So GB mu n indicates what? Energy of transition from alpha state to beta state. That indicates energy of transition from alpha state to beta state. Okay, previously given what is the resonance condition, and this is nothing but what? Resonance condition. This question also given. Okay, sometimes they have given what is the expression for frequency, and GB mu n by h, that is the expression for frequency. Next one from NMR spectroscopy, an AX system. They are given AX system only. So only two types of protons we have. Gave lines at 4.72, comma 4.6, 1.12 and 1.0 ppm. AX type of system gave lines at 4.7 to 4.6, 1.12 and 1.0 ppm away from the TMS using an NMR spectrometer. Away from the TMS using an NMR spectrometer operating at 100 megahertz. Operating at 100 megahertz. What are the values of JAX in Hertz? What are the value of JAX in Hertz and delta AX in ppm respectively? Coupling constant we want to calculate, and delta AX means the difference in the chemical shifts of A and X. And the difference in the chemical shifts values of A and X. Options given 12 and 3.6, 6 and 3.6, 12 and 2.86, 6 and 2.86. Here AX type of system means what? A undergoes couple with 1x, so n plus 1 lines. That means for A we will get a doublet. Similarly for X also we will get one doublet. So we are getting two doublets. We are getting two doublets. This is, let us consider TMS, tetramethyl reference signal. So the signals are observed at what? 1.0. The lines are observed at 1.0. Next one 1.12. Next one given 4.6, 4.72. But delta means what? Midpoint we have to take. Chemical shift means we have to take midpoint. So here what we will get? 4.6, 4.72. Midpoint means what? 4.66. Here 1.0, 1.12 means 1.06. So the gap, that is delta AX. Second question. Delta AX is 4.66 minus 1.06. What will get to 3.6? Okay, delta AX value is 3.6. And what is coupling constant? What is coupling constant? The gap between two adjacent lines. The gap between two adjacent lines. The gap between 4.6 and 4.72 is what? 0.12. Right, 0.12. So coupling constant is what? 0.12. That is in ppm. ppm. But the question is in hertz. What is the instrument frequency given? 100 megahertz. So 0.12 ppm means into 100. So we will get what? 12 hertz. So coupling constant is 12 hertz, and the difference in the chemical shift values of A and X protons is 3.6. That is option 1. Option 1. Okay, next one. This is previous year's question. The vibrational frequency and enharmonicity constant of alkyl halide are the vibrational frequency, nu or omega bar you discussed. We indicated vibrational frequency as omega bar E. the vibrational frequency, and enharmonicity constant we indicated with what? Xe. Of an alkali halide are 300 centimeter inverse and 0.0025 centimeter inverse respectively. Okay, the vibrational frequency and enharmonicity constant of an alkali halide are 300 and 0.0025 centimeter inverse respectively. The positions in centimeter inverse of its fundamental transition and first overtone are fundamental transition and first overtone are in centimeter inverse. Where we will get fundamental transition and first overtone. Options given 300, 600, 298.5, 595.5, 301.5, 604.5, 290, 580. Okay, where we get fundamental transition and first overtone. What is the expression for fundamental transition? Omega bar E into 1 minus 2xen. Almost near to omega bar we will get it. Just below omega bar E we will get. Just below omega bar E. What is omega bar E? 300. Just below 300. Just below 300 means that is given only in option 2. Like that. We can attempt it. Okay. First overtone, if you see, what 2 omega bar E into 1 minus 3xc. Almost double to first overtone. Okay. 2 omega bar E means what will get 2 into 300, 600. Just below 600. Since xc value is very, very small. Xc value is very, very small. Just below 600. That means 595.5. Just below 600, that is 595.5. Okay. Right, next one. The atomic masses of fluorine and hydrogen are the atomic masses of fluorine and hydrogen are 19, 1 atomic mass unit respectively. The atomic masses of fluorine and hydrogen are 19, 1 atomic mass unit respectively. In the bracket it is given 1 atomic mass unit is equal to 1.67 into 10 power minus 27 kg. The bond length of HF is given as 2 angstroms. The moment of inertia of HF is options given 3.2 into 10 power minus 47 kg meter square. Second one 6.4 into 10 power minus 47 kg meter square. 9.6 into 10 power minus 47. 4.8 into 10 power minus 47 kg meter square. So what is the expression for I and for diatomic molecules? I is equal to have what? Mu r square, where mu is what? m1 m2 by m1 plus m2. R is called what? Bond length. Bond length is given 2 angstroms only, but we have to calculate in meters only. 1 angstrom is equal to 10 power minus 8 centimeters or 10 power minus 10 meters. 1 angstrom is 10 power minus 10 meters only, r square. So that you may substitute it. M1, M2 values also given 19 into 1 by 19 plus 120 in atomic mass units, but options given in kgs, that conversion also given. Okay, you may substitute in that equation. You have to get option B, 6.4 into 10 power minus 47 kg meter square. Similar type of question. The C double bond O bond length is given as RCO is given as 120 picometers. 120 picometers in CO2. The C double bond O bond length is 120 picometers in CO2. The moment of inertia of CO2 would be close to. Masses of carbon and oxygen given as 1.9 into 10 power minus 27 kg and 2.5 into 10 power minus 27 kg respectively. So mass is given like this, 1.9 and 2.5, options given again kg meter square. I told you already, in the case of CO2, okay, the molecule undergo a rotation with respect to center of gravity. Center of gravity lies at carbon. Okay, center of gravity is nothing but where the weights are balanced in all the directions. That is called center of gravity. So carbon is considered as stationary. And carbon is considered as stationary. So the expression for I is equal to this bond participate in the rotation, this bond participate in the rotation. So I is equal to mr square plus mr square, will get 2mr square. R is called the CO bond length, and R is nothing but CO bond length. And here, which one undergoing rotation? Oxygen atom undergoing rotation. So here we have to take mass of oxygen atom. So I is equal to 2 into mass of oxygen atom into bond length of CO2. CO. Bond length of CO given 120 picometers. 1 picometer means 10 power minus 12 meters. Mass of oxygen atom is given already in kgs. And you may substitute and the option you have to get 7.2 into 10 power minus 45 kg meter square. 7.2 into 10 power minus 45 kg meter square. So bond lengths of homonuclear diatomic molecules can be determined with the help of both bond lengths of what homonuclear diatomic molecules. Okay, homonuclear diatomic molecules, whether Raman active, microwave active or inactive, microwave inactive, IR or inactive. Okay, how to determine bond lengths of homonuclear diatomic molecule? Options given: rotational and vibrational spectroscopy, rotational and vibrational spectroscopy, rotational Raman spectroscopy, rotational and rotational Raman spectroscopy, rotational Raman and electronic spectroscopy, vibrational and electronic spectroscopy. So we know, easily we can guess from the options. We know rotational spectra, they do not show pure rotational spectra and pure vibrational spectra. So in the first option, if you see rotational and vibrational spectra, that is not correct. The second option also, rotational spectra is given, not correct. The third option, fourth option, if you see vibrational spectra is given, not correct. So therefore, bond lengths of homonuclear diatomic molecule we can determine by both what rotational Raman spectra, they are Raman active. Only which molecules are Raman inactive ones? Spherical top molecules, rotational Raman inactive. Spherical top molecules, rotational Raman inactive. Okay, and by using electronic spectroscopy also we can determine bond lengths. Okay, since whenever we are applying UV visible radiation, electronic transitions occur. The transition of electrons may take place from bonding molecular orbital to anti-bonding molecular orbital. Based on that, we can determine bond length. Okay. So this is given for 4 marks. The symmetric rotor among the following is. What is symmetric rotor? The symmetric rotor among the following is. Options: CH4, CH3Cl, CH2Cl2, CCl4. We know symmetric top molecule. Which one is symmetric top molecule? The molecules belongs to C3V point group and D3H point group. They are corresponding to symmetric top molecules. Out of these 4, which one belongs to C3V point group and CH3Cl belongs to symmetric top molecule? Okay, C3V point group. IA is not equal to 0, IB is equal to IC, symmetric top molecules. CH4, CCl4, tetrahedral point group, they comes under what? Spherical top molecules. It is C2V point group. It may be a symmetric top molecule, and CH2Cl2 may be a symmetric top molecule. IA is not equal to IB is not equal to IC. Spherical top molecule means IA is equal to IB is equal to IC. Okay. Once a question given like this, the microwave spectrum of a molecule, the microwave spectrum of a molecule yields, the microwave spectrum of a molecule yields 3 rotational constants. The microwave spectrum of a molecule yields three rotational constants. The molecule is, okay, prolate symmetric top, oblate symmetric top, oblate symmetric top, asymmetric top, and spherical top. Okay, three rotational constants means three moment of inertia. We know B is inversely proportional to I. Three rotational constants means we will get three moment of inertia. In which case we will get three moment of inertia. Asymmetric top molecules will get three moment of inertia since IA is not equal to IB is not equal to IC. So that is corresponds to which molecule only? Asymmetric top molecule. We know for spherical top molecule we will get only one moment of inertia since IA is equal to IB is equal to IC. Next to symmetric top given. Prolate symmetric top, oblate symmetric top. Symmetric top we have what? IA is not equal to 0 but IB is equal to IC. That means we will get only two moment of inertia or two rotational constants per symmetric top molecules. And prolate means if IA value is less than IB is equal to IC, that is called prolate symmetric top. And oblate means if IA is greater than IB or IC, that is called oblate symmetric top molecules. And generally, prolate symmetric top followed by C3V point group molecules. Oblate is followed by D3H point group molecules. Next question. It is given if reduced mass of a diatomic molecule is doubled, then vibrational frequency of the molecule will be. If reduced mass is doubled, then what about vibrational frequency? Options given: root 2 times to original frequency, 1 by root 2 times to original frequency, 2 times to original frequency, no change in vibrational frequency. So already we discussed for DBR, okay, for DBR and HBR we verified it. For DBR, reduced mass is 2 times to HBR. So what about the vibration frequency? We got 1 by root times to HBR. So similarly here also we get it. If reduced mass is doubled, then vibrational frequency will be 1 by root 2 times to its original vibrational frequency. Okay. By using which spectroscopic technique we can distinguish trans 1,2-dichloroethylene and cis 1,2-dichloroethylene? That is the question given. Trans 1,2-dichloroethylene and cis 1,2-dichloroethylene. Trans 1,2-dichloroethylene, cis 1,2-dichloroethylene. How we can differentiate? Options given: microwave spectroscopy, UV visible spectroscopy, X-ray photoelectron spectroscopy, and gamma ray spectroscopy. If you see, what about net dipole moment for this one? Trans 1,2-dichloroethylene, 0. Net dipole moment is 0. Net dipole moment 0 means this is microwave inactive. Whereas for this net dipole moment is not equal to 0, so microwave active. So therefore, by using microwave spectroscopy, we can differentiate between trans 1,2-dichloroethylene and cis 1,2-dichloroethylene. Next one, among the following, both microwave and rotational Raman active molecule is. Among the following, both microwave and rotational Raman active molecule is. Options given: CH4, N2O, C2H4, CO2. We know centrosymmetric molecules are microwave inactive. So centrosymmetric molecules and spherical top molecules. CH4 is spherical top molecule, it is microwave inactive, as well as it is rotational Raman inactive also. Spherical top molecules are rotational Raman inactive. Okay, this is C2H4, it means centrosymmetric molecule, that means microwave inactive. CO2 also centrosymmetric molecule, so microwave inactive. But what about N2O? N2O, okay, that is not a centrosymmetric molecule, so that is microwave active as well as rotational Raman active. Which are only rotational Raman inactive? Only spherical top molecules are rotational Raman inactive. Next, this is given. The molecule that will show Raman spectrum, the molecule that will show Raman spectrum but not IR spectrum. The molecule that will show Raman spectrum but not IR spectrum among the following is, options given: H2, HCl, BrCl, CS2. So we know homonuclear diatomic molecules are IR inactive, microwave inactive, but they are Raman active. So homonuclear diatomic molecules, H2, HCl. Okay, dipole moment may changes during vibration. Okay, CS2 if you take, similar to CO2. Symmetric stretching vibration may be IR inactive, but asymmetric stretching vibrations or bending vibrations are IR active. Okay, so homonuclear diatomic molecules are Raman active, whereas IR and microwave inactive. This is given in CSF for 4 marks. The G factor of H1 and C13, so nuclear G factor, or it is called as splitting factor, that depends on the nature of nuclei we are taking. So G value for H1 and C13 are 5.6 and 1.4 respectively. For the same value of magnetic field strength, in both the cases B is same. For the same value of magnetic field strength, if H1 resonates at 600 megahertz, C13 would resonate at, the Fresnel frequency of H1 is 600 megahertz. What is the Fresnel frequency of C13? That is the question. Options given: 2400 megahertz, 600 megahertz, 150 megahertz, 38 megahertz. Okay, so what is the relation between Fresnel frequency and G and? So we know delta E, that is H nu is equal to what we have, G B mu N. Okay, mu N is equal to EH by 2 pi MP, that is a constant. B is same, given same magnetic field strength we are applying, that is given. That means nu is directly proportional to Gn. So therefore nu of H by nu of carbon is equal to G of H by G of carbon. So nu of H, Fresnel frequency for hydrogen is given 600. Fresnel frequency of carbon we want to calculate. G value for hydrogen given 5.6, and for that 1.4. So 4 times increase, 4 times gets cancelled. So 150 we are getting. Okay, 150. So G value decreased by 4 times. That means Fresnel frequency also decreases by 4 times, since Fresnel frequency is directly proportional to G. Okay. Next one, this is given. A molecule AB2 shows following IR and Raman spectra. A molecule AB2 shows following IR and Raman spectra. U bar centimeter inverse, IR, Raman, 2215, 1250, 560, VS, PR, VS, PR, S, PQR, S, VS dash. Like this, IR and Raman data is given. The structure of the molecule is, linear symmetrical D infinity H, the bracket, linear symmetrical, bent symmetrical C2V, linear asymmetrical C infinity V, bent asymmetrical CS. Okay, linear symmetrical, bent symmetrical, linear asymmetrical, bent asymmetrical, that is given. Here Q Vs means very strong and S means strong. Vs means very strong, S means strong. Absence of Q branch lines indicates that it is a linear molecule. Q branch lines are absent. That indicates it is a linear molecule. That means not bent. Next, whether it is symmetric molecule or asymmetric molecule, that we can confirm by common lines. And if any common lines are present, non-centrosymmetric. No common lines means centrosymmetric. Here we observed signal in IR, the same signal observed in Raman also. At 1250 we observed in IR, in Raman also. That means common lines are present. That means it is a non-centrosymmetric molecule. That means linear asymmetric molecule. And that is linear asymmetric molecule. Okay, this is given in AP PhD entrance. The NMR inactive nucleus will be, the NMR inactive nucleus will be, the NMR inactive nucleus will be, options given, even mass number and even atomic number. Next one, odd and odd given, even and odd, and even. So we discussed with respect to the number of protons and the number of neutrons in the nuclear spin quantum number. If number of protons even, number of neutrons are even, then I is equal to 0, that is magnetically inactive, NMR inactive also. But here it is given mass number and atomic number. In the case of mass number and atomic number also, if you have even mass number and even atomic number, then nuclear spin is 0. If mass number is odd, nuclear spin is off integral. Nuclear spin is off integral. If both are even, okay, both are even, the spin is 0. Next, one is even, another one is odd. One is even, another one is odd. Then we will get integral. We will get integral. Okay. So, if the mass number is odd, we will get off integral only. If mass number is even, but atomic number is odd. Mass number is even, but atomic number is odd, and third case only. In this case, we will get integral. In this case, we will get integral spin. Okay. If mass number is odd, in that case, we will get what? Off integral. Okay. This is another criteria we have to give nuclear spin quantum number. So we can give nuclear spin quantum number based on the number of protons and neutrons. Another one is based on mass number and atomic number. Both are even, I is equal to 0. If mass number is odd, off integral only. If mass number is even, next atomic number is odd, then we have integral spin. This is given for example. How many normal modes does the CO2 molecule have? Okay. What if the carbon and oxygen atom were constrained to move in one dimension? If carbon and oxygen are restricted to move in one dimension only, then how many normal modes of vibrations we have for CO2? Generally for CO2 linear molecule 3n minus 5, so 3 into 3 9 minus 5, that is 4 normal modes are possible. But if they are restricted to only in one dimension, in one dimension means only stretching vibrations. How many stretching vibrations are possible? 2 stretching vibrations, n minus 1, 3 minus 1. Okay, 2 stretching vibrations. One is symmetric stretching, another one is asymmetric stretching. Okay, what is the question? And if carbon and oxygen are restricted or constrained to move in one dimension, then what is the normal modes of vibration of CO2? That is CO2. 2 only. Okay, bending vibrations we don't have to consider. Okay, bending vibrations we don't have to consider. Okay, this is given different. H1NMR spectrum of a compound gives a doublet and a septet. H1NMR spectrum of a compound gives a doublet and a septet. Which of the following is true? And which of the following is true? It contains CH3, CH2, CH2 group. It contains CH3, CH2, CH2 group. Okay, bonding connectivity is these 3 signals we will get, but here given only 2 signals. Okay, the spectrum consistent with CH3 taken twice CHCl. This is given. Next one, it contains CH3, CH2 group. Next one, it contains CH3 taken twice CCl2. Here all these 6 protons are same, so here we will get only 1 signal. And here we will get only 1 signal, so that is not correct. Here we will get 2 signals, but for these 3 protons will get what? Triplet. For these 2 protons will get quartet, but doublet, septet is given. Here what about all these 6 protons are same, and all these 6 protons are same, so this is A type of proton, this 1 proton is B type. So for these 6 protons what will get? Doublet. For this single proton will get what? 1 plus 6 and 7, that is septated. So it belongs to what? CH3 taken twice CHCl. Okay, like this question is given in it. For example, C5H12 is given. It shows 1 signal in the H1NMR spectroscopy, 1 signal in the H1NMR spectroscopy, but 2 signals in C13NMR spectroscopy. 1 signal in H1NMR spectroscopy, but 2 signals in the C13NMR spectroscopy. The compound is options given: pentane, 2-methyl butane, 2-methyl butane, 2,2-dimethyl, 2,2-dimethyl propane, 2,2-dimethyl propane. Cannot tell without more information. Cannot tell without more information, that is given. So in H1NMR signal, only 1 signal means only 1 types of protons to be presented. Directly I am explaining with option 2,2-dimethyl propane. So what about the 2,2-dimethyl propane? This is 2,2-dimethyl propane. All the 12 protons are same or not? All the 12 protons are same. That means we will get only 1 NMR signal and only 1 MR signal. But how many carbon atoms are there in here? All these 4 carbon atoms are same, A type. This carbon atom is different, B type only. So that means in C13 NMR, how many signals we will get? 2 signals we will get. So option is 2,2-dimethyl propane. This is given in IIT Germany. The number of vibrational modes of CO2 molecule that are detected by IR spectroscopy is. How many vibrational modes of CO2 we can detect by IR spectroscopy? For CO2, 4 vibrational modes are there: symmetric stretching, anti-symmetric stretching, 2 bending vibrations. But out of 4, symmetric stretching is what? IR inactive. Symmetric stretching is what? IR inactive. That means only 3 we can detect based on IR spectroscopy. So the number of vibrational modes that we can detect based on IR spectroscopy for CO2 is, that is 3. Symmetric stretching is what? Inactive. This is also previous IIT JAM question. The total number of degrees of freedom of HBr molecule, total number of degrees of freedom of HBr molecule, okay, which is constrained to translate only along the straight line. Okay, it has to undergo translational motion along straight line. Straight line means in one dimension only. It has to undergo translation motion in straight line only. But there are no constraints on rotational and vibrational motion. But there are no constraints on rotational and vibrational motion. Options given 6, 5, 4, 3. So the number of degrees of freedom possible are 3n. So number of atoms, that is 3 into 2, 6. 6 degrees of freedom are possible for any polyatomic molecule. Out of these 6, 3 are translational motions. 3 are translational motion. One is 2 are vibration. One is vibrational motion, another one is one is 2 are rotational motions and 1 is vibrational motion. Okay, 3 are translation motions, 2 are rotational motions and 1 is vibrational motion. Okay, so 3 number of vibration motions 3n minus 5 are linear molecule. 3 into 2, 6 minus 5, 1. Okay, for any molecule, how many translation motions are possible? 3. X direction, Y direction, Z direction. So the remaining 2 are rotational motions. Okay, but here what is the condition given? It is allowed to move, undergo translation motion one dimensionally. So we have to subtract 2 translational motions. We have to subtract 2 translation motions. That means how many degrees of freedom will get? 4 degrees of freedom. Since that is allowed to only move in one dimension, so that possesses only one translational degree of freedom. So option 3n. Okay. Like this, you may verify. So some other questions you may verify. Based on Lambert's-Beer's law also, they are giving direct questions, and I already have given formula for Lambert's-Beer's law. Based on that also, you may cross check. And observance is equal to epsilon CL log I naught by IT, or that can be written as minus log T, where T is called transmittance, or that can be written as 2 minus log percentage of T. Percentage of T means transmittance we expressed in percentage. So these are the various expressions we have. A1 by A2 we can write as C1 L1 by C2 L2, or log T1 by log T2, or 2 minus log percentage of T1 by 2 minus log percentage of T2. Okay, based on this, these equations also they are giving questions, and in various competitive exams we are getting questions based on Lambert's-Beer's law. That is also important. So you may verify some questions based on Lambert's-Beer's law also. I naught is what? Intensity of incident radiation. IT is intensity of transmitted radiation. Okay, right, and thank you. All the best for your exam. Thank you.